let's visit the first rule. The first rule is the influence of the temperature, and I can realize you to show you it on the slide. Yeah, you see here on the slide, it's not in the Middle Age. You must be. It's no problem. There's no person sitting in. Yeah? It's a normal fire, and you know what's the matter if we put polymers to the fire. Yeah, it's at normally the end, and so you see one idea, or you see the first thing. We have a borderline, a temperature borderline. Over this borderline, we cannot go, else we destroy the polymer parts. Yeah. That's clear for everybody, I think. And now I want to give you some information, some better ideas how we can work with it. You see here some areas, and I used green, yellow, and red. And if you go by traffic, you know what it means. Red is destroying, yeah, the decomposition of the polymers. You see that thermoplaster have also anywhere a decomposition where you also can destroy the melt. It's no problem. You cannot realize a thermoplastic gas. Yeah, it's clear. Everybody understands it. Rubber and thermosets, it's also, and the interesting thing is that we see here for the thermoplastics that we have a region where we can deform it, yeah, where we can realize the deformation, and that's the point where we can realize a thermoplastic processing, yeah, and the other polymer materials, the rubber and the thermosets, they don't have such a temperature, where we cannot realize melting stay, and so we come from a solid state to the decomposition for rubbers and for thermosets. But the borderline for high temperatures, that's not all. We also have a borderline in low temperatures. You know it very well for the rubbers. Yeah? If we go over the glass temperature, under the glass temperature, the rubber is no more elastic. Yeah? There is an experiment, maybe you know it, where the professor puts the rubber into a cold state gas, yeah, where there are minus 200 degrees, and then he is knocking it with a hammer, and everything is pushed away. The problem is that no students becomes ill, yeah, that everybody stays healthy because it's such like glass, yeah, absolutely. The rubber, which we know where we can deformation realize, if we put it in the cold state with the hammer, it's destroying such like glass. And that's why there is the yellow color, the brittle state, or the glass state. It's yellow colored because what's the matter? If we have an application and cooling down it, the geometry stays. Yeah? If you become hot again or warm again, yeah, the geometry stays and we can use it again. Or else, if we go to the other borderline, if you have an application, a part, and heat it up, then geometry goes away. Yeah? That's why the colors. I think with this picture we can show you how the polymer, how the temperature works on the polymer, and you see it in one picture. And I hope that you get if you learn this picture, that you have ideas what all is working there, yeah, and you can very good tell me which processes, which physical things are possible in the polymers. Okay, let's go to the next slide. Here I show you what's the matter with the polymers. You see, for everything you must pay. And you know we have different polymers, and some polymers are cheap, some polymers are expensive. And I was make a diagram where I put on the different polymers, and you see what's the matter. You see here the PVC. Interesting is that PVC have a relatively high rate, yeah, and it's a little bit higher than the polyethylene. And I was say, okay, I want to have an application. I was think that the volume is more interesting, yeah. And that's why I set on the PVC a little bit under the PE. The prices are about the same, yeah. What's interesting, you must know, if I want to have the borderline for maximum temperature to higher temperatures, then I must pay more money for the polymer. One especially thing is, for example, here the PTFE, yeah, the Teflon. You see it's lying a little bit under. The problem of the PTFE is the processing. Yeah, processing of PTFE is not possible to realizing it in the melting state, and that's why you get higher costs than with the processing. Some economics maybe are very happy. Okay, you can take PTFE; it's much more cheaper. The material costs are cheaper. The costs come then in the processing. Yeah, and that's why I have here, if you see it exactly, I have here the line, a broken line. Yeah. The idea is, yeah, if I want to have a high temperature application, I must use a high-cost polymer material. That you must know. Yeah, it would be very nice if you could realize the application where you don't need such a high temperature for this application. Yeah. Here I show you the next thing that are not only borderlines. We have also that the properties depends for the temperature. You see here the tension about the elongation, and you see it depends absolutely for the temperature. Yeah. And so you cannot say, okay, I'm designer, I go to a book and say, okay, this is my material constant. That you cannot say. Yeah? You must always know what temperature you need for the application. And that's the problem, to know which temperature you need in your application. I often make a little, may I say, game. Yeah, I ask the students, look here, we have a water for cooking water, a machinery, yeah, to prepare tea or so. Yeah, which borderlines of the temperature would you say? We are relatively fast on the way to say, okay, 100 degrees, it's the borderline to high temperature. The problem is the borderline to low temperatures. Yeah. Borderline to low temperature, one say, okay, 20 degrees, no, never, it's colder in my kitchen. The other say, oh, maybe 0 degrees, yeah? Then the water becomes to ice. And the other one says, oh no, we are living in a tent, or what does I know, yeah? To make in the camping, yeah? And there are minus 20 degrees, and I must go to organize water on the lake, and then I want to cook it. What's right? The problem is a product which is right for everything, it will be cost anything. Yeah? And the most cheapest will be this product, where the students say, okay, in my kitchen 20 degrees, everything is okay. Yeah? Then we can use polypropylene. Yeah? And polypropylene has the problem that if we get under 0 degrees, yeah, there is a stay collection. Yeah? There changes the stays in a solid state phase, yeah? And that we must know. And so we can use polypropylene, but it's a problem if we want to have it for minus 20 degrees. If it's knocking against a stone with the thing, yeah, then it can be broken. Yeah? And so you see, a good thing must cost it. That you must say, okay, I pay for this. Yeah, so it is. The next question here, you see how much it depends for the temperature, and the question what you must say is, what does I need? If you see from 20 till 80 degrees, yeah, it's a big region where the polymer constants, where the material constants are in. But if you want to take to minus 20 degrees, this window will become more bigger. Yeah? And so you can use the material. If you want to say, okay, this big window, you need more material to use the full material opportunities. Yeah? Okay. That means there are not only borderlines, there are also between the borderlines a big depending on the temperature. Here I give you some temperatures and their influence for the deformation. What we have is the a coefficient which says how the length is depends for the temperature. Yeah? And that I want to show you here with this picture. And you see the interesting things here in this region where the polymers are coming. Yeah? Interesting is it, you see also a triangulation a little bit, yeah? Some triangles. And that's depending not only from the polymer as a chemical substance, it depends also from the input, yeah, from the fillers and so on, yeah, and that's why you get such a triangle. And you see it's the quality is very high, and then you have big differences in this quality that you must know. And the problem is if you want to connect polymer and metals, yeah. You see in this slide that the elongation for high temperature of the polymer is much more higher than this of the metal, and that will realize as tensiles. Yeah? And we get big problems if we want to connect polymer and metals, and we have also some processes where we are realize a collection of polymers and metals, and we must know some tricks. Yeah? We need some tricks that we can realizing a good connection between, that we can reduce the tensiles. Okay. What else we see? For example, if we are realizing polymer applications for our cars. For example, a door of the car, yeah, and we put it in to a metal skeleton of the car. We see that the door works for high temperatures, and you know, everybody comes from another country. You know, in the tropics, yeah, or in the where it's very hot, the weather is very hot. Yeah, in Arizona, for example, you have more than 100 degrees if it's standing in the sun. Yeah. Otherwise, we have minus 40 degrees in Scandinavia, for example, or in Russia. And we need especially ideas how we can realize the work of the materials, yeah. And then we have the idea that we don't give the parts stand by stand. We give it after array, yeah. And so it can realizing a little bit temperature influences to wax, or we can also use a rounding on, and then the rounding is a little bit bigger, yeah. That are the two ways to realizing it. Okay, here I have a slide which I had been took on a swimming pool, and you see what's the matter there, yeah. There's a polymer part put into a stone, and they are join it for, let me say, 15 degrees, yeah, normally weather. And then they are heating up the swimming pool to 30, 35 degrees, and it works. It works not very good. It works the material, yeah? Okay, that's a slide for your impression. So here I give you some ideas how you can realizing the different elongation of the materials. You see in the red color the polymer, in the blue color the metal, and you see the blue and the red temperature. Blue cold normally, hot, red hot, as you know it from the water, yeah. And you see that the polymer takes a more bigger elongation, and we have the opportunities, two opportunities I want to show here with this slide. First opportunity is to realize such as a bridge, yeah. And if it's hotter than the bridge goes in, and the other opportunity is to realize a round area, yeah, a rounding on the area, and then it's putting away a little bit, yeah. So that are the opportunities. If you want to realize application, you can bring it to your design. And we have in German two words for the design. One word is the Konstruktion, the other word is an overtaken, is design, and we understand it in the kind of art. Yeah? And if you see the last opportunity, yeah, that can realize you a new kind of art to realize a design, yeah? If they are round and nice touchable parts, applications from polymers. So here I want to show you what's the matter if we go over the borderline of high temperature. You see in the first case, you see the cold application. In the second place, you see a heating up, yeah? And number 3 shows you what's the matter if it's cooling down. Then you see a little bit of the deformation is staying in the part. Yeah, that's different to the metal. If you have a normal metal, yeah, without any other substance, and we want to melting it, it's become hotter and hotter and hotter. Then it melts as ice, yeah, as water ice. It goes to the melting state, and it's a liquid absolutely, and it's away. And the polymers, they hold a little bit the geometry, yeah. And after melting, they are reactivate their geometry, but a little bit stays. It's the problem of the theory of deformation of polymers. And I wish you much luck if you hear it from the physics. Here you have the application, what it means for a real part. So here I have some ideas what we can do. The first thing is the question, how long does the hot temperature works? Yeah, because the polymers are very good isolators. Yeah, the isolating properties are very well. That's why we hold a cold core, and the cold core stays in the position. Yeah, and so it's possible that we get a short time. We can realize a short time to overheat the polymers without that there are problems come. The next slide shows us resistant fillers. For example, glass fibers also. They bring us about 5 degrees, what we can realize to go over the polymer, over the melting temperature, the borderline temperature. Only about 5 degrees. It could say, oh, that's not much, but if you think what the prices are, yeah, if you need another and much more better polymer, for example, if you can use an, let me say, an polyamide against to a polyimide, yeah, then you have big difference in the prices, and you say, okay, I take the filler. Also interesting is that the fillers are realizing a short time overheating more better than a material without everything. In this picture, you see an idea that we get, for example, a metal or another material down, which is staying the temperature, and the polymer gives other ideas to realize the design, for example, a soft touch or so. Yeah, we could realizing an skeleton for metal, yeah, and overlay polymers, and then we can realize a little bit more high temperature. So we have a second material to realize the application. And the last picture here, you see we have a hot, medium from one side, and from the other side a cold layer. And sorry, this application is realized, for example, if you want to have a bottle. Yeah, if you want to fill in a bottle with the hot medium, then you have a cool region outside, hot material inside, and you can realize for a short time an overlay. If you want, for example, if you want to have it to fill in a squash, yeah, you must heating up that the bacteriums are killed, yeah, and you can put the bottles into a cold water, yeah, and fill in the hot medium, and it's the cool water from outside is cooling, or stays the state of the bottle, the geometry of the bottle. So that we saw, you see here the last picture. I hope that you had got a little impression what temperature and high and low temperature can realize with polymers. I must tell you a little appendix. Also, the time which is working on the temperature is a very interesting thing. You will realizing it if you learn the physics of the polymers. They have very especially methods to realize the dependence of temperature and of time. And you must know, if I use a material very often, it you need much more better material than you use it only short times. Thank you for stay. We are through this lesson again, and we go back to the slide here of the 10 rules.